Hello everyone, and welcome to this training course and this lecture about convolutional neural networks. I'm Maria Luisa Taccari. I work at ISNWF, and I'm gonna present this lecture with contribution and materials from my colleague Vera. If you have any question, you can drop me an email, and let's get started. So in this lecture, this is the outline for the lecture. We start discussing the motivation for convolution, then discussing what a convolution is and the arithmetic behind it. We will then go into building a convolutional neural network. And finally, we will review some popular CNN-based architectures. So let's start with the motivation for convolution. So model deep learning relies on architectural choices, and CNN are a perfect example from that. So let's start by looking at what really motivated convolution. The reason for that was that MLP, which is multi-layer perceptron, were simply too expensive for it. So in principle, they are universal approximators, so they can represent any function. So why would we bother? Well, they can, but they would be very expensive, and actually it was even shown in the past that it was not enough. So before CNN, it was training large neural network for vision was infeasible. And that's why then researchers had to come up with the CNN, so to actually build some architecture with inductive bias made for images. So eventually, this means that if you can encode inductive biases, which is assumption about the data, into the neural network, you can in this way constrain the hypothesis space. So effectively, you can learn with less data and less computation. But that's not only about the compute time, but that's also about optimizations, because this architecture shaped the loss landscape, making it good solution, also discoverable. So if in principle it is possible to represent the solution with MLP, it is actually very difficult to optimize. And CNN made the optimization much faster and much easier. And also constraining the hypothesis space, so adding these inductive biases, also help preventing overfitting. So which structures do images have? Let's look at this example of some numbers. And what we're going to see is the first one is spatial locality. So it means that to make sense of a pixel, we only need to look at the surrounding pixel. For example, in the second image from the left, you see this blue box. And in order to define the edges of that area, of the properties of those areas, you only need to look at those pixels, not the pixel, for example, in the yellow box. The second one is compositional structure. So it's simple features, for example, edges, that combine into more complex feature. And that's becomes easier to understand if we, for example, think about this sketch of a cat and how these simple lines define actually the structure of the cat. So let's stay with cats and let's look at these other properties that images have. And so a concept of translation invariance means that the output remains the same even if the input shift. So the cat is still the same even if it's moved over the image. When translation equivariance, that is really a property of CNN, means that if you shift the input image, also the output is shifted. And again, CNN are designed to exploit this second concept, the translation equivariance, which is also crucial for tasks like object detection. So again, what's just a recap, what structures do images have? So they have locality, which means that's nearby picture for meaningful local structures. They have compositional structures, so simple feature combined into more complex feature. And this we will see in CNN. This pretty much comes with like stacking different layers of convolutional layers. Will give us this compositional structure. And translation equivalence means shift the input, shift the output the same way. So we want to have a network that has this property, that perform these properties, and has eventually a localized translational invariant aggregation. Which means, again, the architecture needs to suit the problem because of induction biases. And actually, we will see that will be solved by having this sort of sliding filter that look at like the local pixel, but actually sliding over the image to maintain translational invariance. And then stacking many of those filters will also give us compositional structure. But let's get into the concept. What is actually a convolution? So let's look at this summary of a convolution. Let's start from the input image. So we have an input image here, which is a blue image. For each of the pixel, we have a value, no? And then we have a filter, a kernel of a filter, which is this gray box. And the composition of the two will give us an output activation map, which is the green box. Eventually, the idea is simple. We place the filter on top of the image, and then we multiply. So we have a dot problem. We multiply each pixel of the filter with the pixel of the image. Then we sum them up, and we get a value. And that is going to be the corresponding value in the output activation map. Then we slide the filter one step. So we slide it over the image, and by doing so, we get all the different values of the activation map. So by doing so, what we're actually doing, we are sliding this learnable filter over the input. So the filter is not fixed, as in this example, but actually the weights are learned during the training process. And by combining dot products at each location, we are learning an output activation map. But this is actually a concept that was already there in computer vision. The only difference was that previously these filters were not learned, but were just fixed. So, for example, we have Sobel detectors that look, for example, at vertical lines, so different features of the image. So now the difference is that these kernels, these filters, are not fixed, but again are learned by the network. So if we go back to the convolution versus MLP, a concept we've already spoken about before, if we would use MLP, we would have to flatten first the image into a very long vector, and then we would have a very large layer, which would need to learn those relationships. Of course, this would scale poorly with image size, and it would also be a quite ineffective use of the weights. Whereas with CNN architecture, we are utilizing the induction biases of the images, and we can therefore have a much smaller neural network, which also means that the weights are then seeing more of the images, so represent more pixels of the original images. So in that sense, they are better and more suited for images. So let's look a bit at the output arithmetic. So what does the output feature maps depend on? And let's look at a few of these concepts, like the kernel size, the padding, the stride, and eventually all the parameters that are used to design a CNN architecture. So what does the output of the activation function look like? So they depend on the input size, the kernel size, the stride, and the padding. So this control how much spatial resolution is actually preserved or how much it is reduced. So the stride is control how much the filter moves at each step. So a stride of 1 means that the filter only moves by 1 step at a time. Stride of 2 means that it actually skips pixel by moving with a stride, with a step of 2. In this way, you can imagine with a higher stride, the higher the stride, the more downsampled the image is. So eventually the stride affects the output of the feature map. And then you also have padding, which actually, because you can imagine that by having this stride, you could actually arrive towards the output. So the problem is that you're running out of the image. And by having a padding, you're actually adding some pixel around the image. Or you can add no pixel, and that's known as the padding 0 or valid padding. So the filter only stays within the original bound. So the outputs shrink, and you lose information in the border. Or you can put padding 1, in which you add 1 pixel white border on the of 0. And this reconfiguration is referred as same padding. So because if you use actually in the situation you use a filter of 3x3, because it allows you to center the filter at the edge, at the border of the image, and in that way you have an output that will result in an output which has the same size of the input. And you might want that if you want your output activation map to have the same size of the input, which, for example, we will see later is a desirable condition when we have skip connection or concatenation. And what about depth? So RGB images have 3 channels, red, green, and blue. So how does the filter work in the different channels? So you have actually one filter with 3 kernels. Each kernel works at the different channel. What you then do, so you calculate them separately, then you sum them up, and then you get one output. So you add the bias, and then you add one output channel. So that means that the number of filters that you define defines the output channels in the resulting feature map. Because, for example, in this example, we only have one filter, so the output's feature map will only have one channel, one output channel. But you might want to have different views of the same image. So, for example, this filter might now be looking at vertical lines, but you would want one that focuses on other characteristics of the image. Hence, you would use different filters which work with these 3 kernels that work in parallel, and then get summed up. And by controlling the amount of filter, you're controlling the size of the output, the depth of the output's activation map. Okay, we have defined now the components of the convolution of CNN. But let's look into the neural network now. So CNN involves stacking convolutional layers, nonlinearity, and pooling layer to aggregate feature properly. So in a standard CNN, it's built on an alternation between convolutional layers and pooling layer. We can think about the first part of the network, which is composed by convolutional layer nonlinearity and pooling layer that we will see. We'll have it's a more general part of the network, and then we have a task-dependent part, which will depend on what the task is. So is the task classification, is segmentation, is regression, and so on. But let's look now at what pooling is. So the idea, so pooling works in a very similar way to filters. The only difference now is that you are not learning weight, but you're actually using this filter to aggregate information through an aggregation function, such as maximum or average. So you would have max pooling or average pooling. And the idea of that is that you can downsample in that way your input. So you reduce the height and the width, but you keep the same number of channels. So you are downsampling the image. So what you see in this image is that's a typical example of CNN, in which you have this blue layer, which are convolutional layer, which is the one we saw earlier with the filters. Then we have some this other pink layer, which are downsampling the image through pooling operations. And then you have this concatenation and stacking of convolutional layer and pooling layer. And in this way, we are, by shrinking the height and the width, you are forcing the network to look at larger and larger regions of the original input. And in this way, you're actually forcing and allowing CNN to learn hierarchical and features. That means that in the initial layers, you are learning more lower level and, let's say, superficial features. But the deeper you go, the higher level information you're actually learning, and that's again because you are shrinking the image, so you're actually focusing on those higher, more abstract level of representation. So if we summarize a bit what we have discussed and how CNN work, we have first the property of the image property of locality, which we address using this shared filter. So we have filters that are quite localized, but then are shared across the image. And so they detect really local patterns like edges and textures, and rather than being overwhelmed by global patterns. Then you have the idea of translation equivalence, which means that if you shift the input, the output is shift. And that's really obtained by having these sliding filters, which ensures that the property is maintained. And finally, we have the compositional structure of an image, which is reflected in this stacked layered architecture of the network, in which deeper layer tend to learn higher level abstract feature of the image. In years, CNN evolved significantly, and for example, there was quite an important competition that was called ImageNet. If you look at this at the arrow through the years, you see that between 2010 and 2017, we have a radical transformation of what happened. So at the beginnings, the error rates were quite high, And then in 2015, we have, in 2012, apologies, we have an important kind of revolution with AlexNet. And that sparked a rapid descent of error. And then only in 2015 when the error becomes lower than the human error. And why did we get that progress? We got it by having always deeper and deeper layer. So we got at that time by more than 20 layers. However, you could see that if we kept increasing the number of layers, such as we see this 150 layers, the error would at a certain point would start rising up. And so again, there was a new model that came out, which was ResNet, which introduced the idea of residual connection, which really helped reaching an even lower error. So let's look into these residual connections. Residual connection means that, or skip connection, is a way in which you allow the input to bypass some layers. So you are pretty much copying over the input. In this way, the network is forced to learn only the residual, as ResNet's saying. So the problem was that in every layer, the network was forced to learn a brand new transformation, and in this way, having actually this residual connection allowed to go to deeper and deeper network. So from 20 to 100 layers and 1,000 of layers. And because adding these shortcuts made optimization much easier. So the loss function, the landscape is much smoother. So as you can see in this visualization, without the skip connection, the loss landscape would be quite difficult and quite rugged, and the optimization process would get stuck in some local minimum. Whereas by adding this skip connection, you add more stability and you have a smoother landscape, which allow easier and faster convergence. So this idea of skip connection was then reused also in another famous architecture, which is called UNet, which was initially proposed for segmentation in the medical domain. The idea of UNet is again to use the skip connection. However, in a bit of a different context. So let's look at the architecture. We have a first part, the left part of the network, which is downsampling the image. So it's getting deeper and deeper representation, but shrinking the spatial dimension of the image. And you can and that's usually called the decoder of the image, until you get to this deeper part, which is kind of the referred as the bottleneck, in which you have a very small spatial dimension, but a very deep representation. And then what again you do, you upsample. So a different way to do upsampling, but it's pretty much the inverse of downsampling. And you recover that initial spatial dimension in order to do, for example, segmentation. But of course, by doing that, you are actually you're losing a lot of spatial information. In the decoder part, you have lost all your of the spatial information that you had at the beginning. So optimization becomes also much harder. And that's why we have this skip connection, which are the horizontal lines the gray lines that you see, which connects from the left to the right. So they pretty much copy and concatenate the inputs from the encoder to the decoder. And then this UNet architecture was then used in a lot of variety of tasks and disciplines as well. And to conclude, CNN are the base of a lot of popular architectures. So you can find them in a lot of different architecture again, but you can also tweak them for the task that you have in hand. So for example, if we are thinking about the Earth, so and the geometrical, the spherical geometry, you wouldn't want to add a padding of 0 on the border of the image, but you would want to add this so-called periodic convolution, so that when you actually get from the data from the far right are actually copied to the far left, so that the representation is actually continuous. And secondly, if you have spatial temporal data that you want to work with, then you are thinking about a combination of some spatial neural networks like CNN and some temporal neural networks, so some neural networks that have inductive biases for temporal data. And so one example of that is convolutional LSTM, in which the operation inside the LSTM are actually replaced. So the matrix multiplication in the LSTM are replaced by a convolution operation. But again, there are many more examples. And if you want to know more, I recommend you some lectures here that I've also been using in this lecture. Thank you.